Hey everyone, welcome back to Probability Theory. This will be lecture 18 of the course. And in this section, we're going to discuss the next interesting discrete probability distribution, and that is the hypergeometric distribution. So let's take a look at that. And we'll call this section 2.7, the hypergeometric distribution. And so this one's a little different than what we've seen previously. And so let's kind of talk this through. The idea here is, let's suppose that we have a population that contains n elements. Okay, so we have a population containing n elements. And I'll just use capital N here to denote the population. Okay. And let's suppose further that every element in the population possesses one of two characteristics. So each element is either, we'll just say, red or black. And we say red or black, or yes or no, or on or off, or up or down, or whatever. All right, so each element, there are two characteristics of interest, and each element has exactly one of them. Right, so in this case, we're saying red or black. Okay, and so we'll specifically assume that R of them are red, and B equals N minus R are black. Right, so you have, obviously, B plus R is N, right? So everyone is either red or black. Okay. Now, the goal here, the sort of experiment here, is you're going to reach into this population and you're going to select a certain number of elements randomly. Okay, and so we select little n elements randomly. Okay, we select little n elements randomly. Okay, and then the random variable in this case, y, is going to denote the number of red elements in the sample. So let y is going to denote the number of red elements in the sample of n. Okay, right, and so y has a hypergeometric distribution. Y has a hypergeometric distribution. So this is the idea. I've got a population, right? And I'm just going to actually draw a little picture here. I got a population. It's like an urn. In this case, it's a big bucket. And inside of it, I've got R reds. And I've got N minus R blacks. Right? You can just think of these as little like balls. Some of them are red. Some of them are black. Right? So some of them are black and some of them are red. Right? Okay, and we reach in there and we select n elements from the total of big N elements. Okay, we then count the number that are red and assign that to our random variable y. So that is what's happening here. It's very simple, actually, right? But that's why it's powerful, because it's so simple that it can apply to about a billion different situations. Okay, so how are we going to think about the probability distribution? Well, the total number of possible, so you can think of this basically as, hey, I'm going to reach in, I'm going to grab n items, right? And some are going to be red, some are going to be black. Okay, And there's going to be a whole bunch of different possibilities, right, depending on how big the population is, right? But the total number of possible samples like this is what? Well, it's n choose n, right? The total number of possible n samples is big N choose little n. Right? I've got 100 things. I'm going to choose 10 of them. All right, so that's straightforward. Okay. And so let's say that we draw a particular sample. All right, let's say we're interested in the sample that has 4 reds and 6 blacks. Okay. So in this case, n is equal to 10. And let's say big N is 100. Okay, and let's say that in the big N, 60 are red. And 40 then are black. Okay. So how many different samples are there going to be that have 4 reds? Well, you can really just think of this as the MN rule. Okay, so to find out the number of reds, I just take 60, choose 4, right? There's 60 total reds, and I'm going to choose 4 of them. Right, and then the other piece of the sample has to be all blacks, and there's 40 of those, and I'm going to choose 6 of them. All right, so this is just M times N. Right, remember your combinatorics, your M times N rule. Okay. And so in general, what have we done here? In general, all right, so let's remember our situation. We've got big N equals 100. All right, little r equals 60. Those are the number of reds in the population. Okay, and our sample size is 10. Okay, and so the number of ways to draw samples of 10 items from the urn, where 4 of them are red and 6 of them are black, is we said 60 choose 4 times 40 choose 6. Now what's really happening here in general, we're saying it's R choose Y, right? R being the number of reds in the population, the number of items of interest in the population, Y being the number you specifically want to have in your sample. And then over here, instead of 40 choose 6, let's put this in terms of N, R, and Y. So this would be N minus R, right? So you got your, so if 60 of them are red, then 100 minus 60 are black, so 40. Okay, and then if I want if I want 4 reds, then the number of blacks I implicitly want is N minus Y, so 10 minus 6 equals 4. Or sorry, 10 minus 4 equals 6. Right, and so this is just how we would generalize this counting. Right? Now, since each sample in the population has equal probability of being selected, then the probability here would be equal to basically 60 choose 4 times 40 choose 6. That's how many samples are of the desired type, times the probability of each of them, which is 1 over, remember, big N choose little n, so in this case 100 choose 10. Right? And so in general, right, we kind of use this as the blueprint for the hypergeometric probability distribution. And so let's define that now. Okay, so a random variable y is said to have a hypergeometric probability distribution if and only if the probability of y is equal to r choose y times n minus r choose n minus y, little big N, little n, all divided by n choose n. Okay, and we'll have to say here that y will have to be between 0 and n naturally. 0, 1, 2, up to n, right? You can't have more successes than you have samples, right? So if I sample 10, I can't have more than 10 successes, obviously. And so specifically that would just imply that y is less than or equal to r. Okay. Well, also, yeah, y must be less than the total number of successes in the population. So y is less than or equal to r, and also n minus y, right? The number of failures in the sample has to be less than or equal to the number of failures in the population. Okay. Very good. So that's the idea here. That's the idea. We want to sample from a population with a known rate for a desired characteristic, and we want to be able to quickly say what the probability of getting a certain number from that population with said characteristic. We want to know that probability. That's what the hypergeometric probability distribution tells us. Okay, let's do an example. Okay, let's do one of our urn examples. All right, so let's say we have an urn with 25 balls in it. I'll just draw the picture rather than write it out. So big N is equal to 25. I got 25 balls in it. 20 are red and 5 are black. 20 red, so that's R, and N minus R equals 5 black. So I got 20 reds, 5 blacks, 25 total. Okay, here's the question. What is the probability? What is the probability of selecting 5 black balls if 10 are sampled? What is the probability of selecting, I'm going to say 5 red balls. Well, I'll say 5 black because that's what I have written down. 5 black balls if 10 are sampled. And so I actually wrote this a little bit backwards here. So here is our, so in this case, our R is 20. Yeah, no, I had it right. R equals 20, and N minus R equals 5. Okay, so let's kind of write out all the information that we have. So our big N is 25. In this case, R is equal to 20, and N minus R is equal to 5. Okay, and then our sample size is 10. And so what we would say here is that Y is hypergeometric. So we would denote that by just hypergeo or geom. And then what do we need? The parameters are we need the total population size, and we need the number of successes in the population, and we need the size of the sample. And I do have this backwards. I apologize. I want the probability of selecting 5 red balls if 10 are sampled. Okay. All right. All right. So let's see here. What is the probability of Y equaling 5? Okay. And so we know the distribution says it's R choose Y. R choose Y times N minus R, population N, choose sample N minus Y, right? All divided by N choose N. And so this is 20 choose 5 times, so N minus R, that's 25 minus 20. I'll just write it in here, 25 minus 20, and then 10 minus 5, all divided by 25, choose 10. And so it looks like this. All right, and we can easily sort of figure out what this is all about. So this is 20, choose 5, and then it's 5, choose 5, right? And then it's 25, choose 10. So really you just have to kind of go through here and run the numbers on these factorials and kind of do your cancellations. But I'll tell you, if you do that, you get 15,504. That's the number of ways to choose 5 red balls from 20 red balls total. You're going to multiply that times 1. There's only one way to choose 5 black balls from a total of 5 black balls. And all of that is divided by a big number, 3,268,760, which is the number of ways to choose 10 balls from 25 balls. Okay, and then of course, when you divide this all down, you get 0.00475. And so that is the probability of selecting 5 red balls in a sample of 10. Okay. All right, so that's a nice little problem. Let's do a more straightforward, more practical example here. A warehouse contains 10 printing machines. Printing machines, printers, I guess. And then 4 of the 10 are defective. 4 of which are defective. Okay, not a good rate. So a company wants to buy some printing machines, some printers, and they select 5 of these things at random. Presumably, I guess they're just like in the garage, they're not plugged in. You say, well, I'll take these 5. Okay, so a company selects 5 at random. Okay. I guess they assume they all work. So then what is the probability? What's the probability that all 5 do work? Okay. All right, and so we'll let y be the number of working machines in a sample of 5. Okay, so y is going to be the number of working machines in a sample of 5. Okay, and so in this case, y is a hypergeometric random variable. Right, it's hypergeometric, so what are my parameters? What is the population? Well, in this case, the population is 10 printing machines total. What is the number of working machines? What is how many of those 10, how many represent successes? Well, success in this case is picking one that works. So R is equal to 6. And what is the sample size? N, little n is 5, right? They're going to select 5 of these things at random. And so what we want to know is what's the probability that y is equal to 5. I'm going to pick 5, and I want all of them to work. What's the chances of that, given the situation? Well, let's remember, this is going to be r choose y times n minus r choose n minus y all over n choose n. Okay. And so in this case, we've got 6 working machines. I need to choose 5 of them. And that means the remaining parts are, so 10 minus 6, that's 4, choose 0. Right, I want to pick 5, I'm going to pick 5 machines. I want them all to be working. So 6 choose 5, 6 are working. I want to choose 5 of them. 4 are not working. I want to choose 0 of them. How many different possible selections are there? Well, there's 10 choose 5 there. Okay, and that is the hypergeometric probability distribution. So let's go ahead and actually work this one out. Let's say we've got, what do we got here? 6 factorial over 5 factorial, 1 factorial. Okay, times 4 factorial over 0 factorial, 4 factorial. All divided by 10 factorial over 5 factorial, 5 factorial. All right, so up top, what I got the 6 and factorial and the 5 factorial cancel, and I just have a 6 there. And then, of course, this is just 1. So there aren't many ways to do this. How many, what's my denominator look like? Well, I've got 10 and a 5, those will cancel, so I've really got 10 times 9 times 8 times 7 times 6, and that's going to be over this other 5 factorial, so 5 times 4 times 3 times 2 times 1. Okay, and so on the top I have 6, and the bottom, well, I can cancel some of these away. That gives me a 2, the 4 and the 8, and the 2 cancel away. 2 times 4 is 8, that cancels the 8. The 3 will cancel with the 6, and I'm left with 2. And so really up down here, I got 2 times 9 times 7 times 2. Okay. And so I've got 6 divided by 252. And so there's about a 2% chance of this happening. 0.0238. So not very likely. I'm almost guaranteed to to end up with a broken printer if I go about it this way. I might want to ask to turn them on. Plug them in, do they turn on? Let's at least do that. Okay. All right, so that's the hypergeometric distribution. Let's take a look at the mean and the variance of this thing. Okay, so theorem. If y is hypergeometric with parameters n, r, and little n, then the mean is equal to, of course, is the expected value of the random variable y. It's just equal to n times r divided by population n. Okay, that's interesting. We'll see why that is in a second. What about the variance? Sigma squared, that's the variance of the random variable y. It's equal to n times r over population n times population n minus r over population n. Okay, I guess I put that in there. All times n minus n, population minus sample, divided by population n minus 1. So kind of a complicated variance expression. Okay, so what's going on with these? All right, these look pretty complicated, but if you kind of look closely at this and then you compare it with what we had for our binomial distribution, you see there's a lot of similarities happening. In fact, there's a huge overlap, in fact. So let's remind ourselves of what a random variable that's binomial NP had for a mean, right? So for a binomial random variable, the mean was n times p. Okay, remember that? If not, you can reference it, right? So for the geometric, hypergeometric, sorry. What is the probability of success? If we were going to say that there's a probability of success, how would we characterize it? Well, we would say that the probability of success is equal to the number of successes in the population divided by the population size. So there's, whatever, 10 reds out of 100 total. Then there's a 1 in 10 chance of selecting a red, right? Okay, so the probability of success is kind of like R over N, right? And so if you think about it from that standpoint, then if you start with the mean of the binomial, N times P, well, you can see that if you just sub in this for P, N times R over N, Right? Another way to express that is n times r over n. Well, that's just what we have there, isn't it? Okay, and so that's the same thing basically. So this mean is really the same as the is really the same as the mean for the binomial distribution, right? Just kind of written differently because it's expressed in a different way. Now, what about the variance? Do we get the same kind of thing from the variance? Well, let's think about what's for the binomial NP. What was the variance? The variance was n times p times q, recall. Right, so n, the number of successes, times the probability of success times probability of failure. Okay, so again, if we think about for the hypergeometric, the probability of success is what we said before. It's r over n. Well, what's the probability of failure then? Probability of failure is going to be the number of failures in the population divided by the population. Well, if there's r successes, then there's n minus r failures. Okay. All right. And so that's kind of interesting. And so let's take a look here. So we said that the sigma squared, the variance here was n times r over n times n minus r over n, all times n minus n over n minus 1. Well, this is that. That's n, and there's your p, and this is just your q, isn't it? Right? So you kind of see that we've kind of got that form, npq, but we have this other thing on here. We've got this other little factor that's nowhere to be found. There's nothing here, right? So what is this other little factor? Well, we can kind of view this piece here as sort of an adjustment factor, right? So n minus n over n minus 1 is an, and I'm just going to put this in quotes, it's an adjustment factor. It's an adjustment factor. So when little n is large relative to big N. This is an adjustment factor for when little n is large relative to big N. Right? And so it's really, this piece becomes important when little n is large relative to big N, because you can see, you can definitely see that this ratio, n, population n minus little n over population n minus 1, this thing goes to 1 as the population grows to infinity for a fixed n, for a fixed sample size. N is the sample size, right? So if I have a really huge population, then this is basically 1. But if my population is kind of small relative to my sample, then this is an adjustment. Now, really, the point of this is that when we sample without replacement, we're reducing the variance slightly, as in the hypergeometric. In the binomial, we're basically sampling with replacement, and so in that case, the value is 1. But in this case, in the hypergeometric, you're essentially sampling without replacement, right? We're taking the whole sample out at once. Right, and so this is going to tend to reduce the variance. And that's what that little adjustment factor is all about. Okay, very good. All right, so I think that's a great place to end it. Next time we will talk about one of my favorite discrete distributions is the next one up, and that's what we call the Poisson distribution. And so it's a very cool one, and I hope to see you all then. Until then, take care.